Okay, so we are in the midst of double integrals. We started talking about double integrals on Friday. And so in first year when you did single integrals, you learned them by, the first application you probably learned was the area under a curve. And so when we get to double integrals, now we're finding the volume under a surface. At least that's one application of a double integral. There's lots more important ones actually, but when we're learning double integrals, it's helpful to think of that. So in this particular example, we have, wow, what is wrong with my pencil? 1 second. Okay, that's better. So in this particular example, come back, there we go. We are interested in finding the volume under a plane. And we're given the equation of the plane right here. So that's this surface here is part of the plane Z is equal to 4 minus X minus Y. And we're told to integrate that over a rectangular region R, which consists of, that's this surface here at the bottom, okay? That part of the xy plane between x, where x is between 0 and 2 and y is between 0 and 1. So when we're doing a double integral, we're integrating over some region. When you did a single integral, you integrated over a range of x values, right? You found the integral of fx dx, where x went from one value to another value. You integrated over a range of x values, over a line. In the case of double integrals, you're integrating over a surface in the xy plane now, because there's two variables of integration, x and y. Okay? So it's no longer, we're not integrating just along the x-axis, we're integrating over a region x and y. And last day we talked about, how to think of that conceptually, and how to do that how to do it practically is what we're going to go over today. And we talked about how you can integrate first in the x direction and then integrate in the y direction, or you can integrate in the y direction and then in the x direction. You can reverse the order of integration for any function that's continuous. This is obviously a continuous function. It doesn't have any points of singularity or discontinuity in it. And so we could do that, and we'll look at doing it both ways, okay, in both directions of integration. And we talked a little bit how, if we integrate in the y direction first, well then we would cut this geometrical figure, if you want to think of it as a very misshapen loaf of bread, we would cut it, somewhere at some x value like this. So we would cut through it down like this, along some plane which is parallel to the y-axis. Okay, and then you would look at the end of this loaf of bread, and what you would see is you would see a function, z is equal to a function of y at some particular x value, and you could find the area under that curve using an integral, integrating in the y direction, right? That gave you the area of a slice of this thing, and then you make the slice, a certain width dx, and you add up all the slices in the x direction, which is integrating in the x direction. Okay, so now we're going to do this practically with a calculation. So we want to find the volume of this funny-looking house here, okay? So a rectangular region of integration is really easy because the limits of your integrals are really easy. They're just numbers, okay? So we're going to need x min, and we're going to need x max, and y min and y max. These are the limits of our double integral, okay? First integrating maybe with respect to x, so we need x min and x max, and then we integrate with respect to y, so we need y min and y max, or the other way around. Okay, well it's pretty easy because x min is always equal to 0, and x max is always equal to 2, right? It doesn't matter if when I'm integrating with respect to x, it doesn't matter if I use this value of y, or if I use this value of y, or this value of y. As I pass through this region R at some particular y value, integrating in the x direction, x min is always 0 and x max is always 2. Okay? Similarly, y min is always 0 and y min is always 1. That's what we're told up here for this rectangular region. Okay? And again, if I fix x at some particular value, maybe right here, and I integrate in the y direction like this. Okay, it doesn't matter if I use this x value, or this x value, or this x value. Y min is always 0, and y max is always 1. We'll look at examples next of when that isn't the case, okay? But this is sort of the simplest case. So we've got our limits of integration for this rectangular region. Because it's a rectangular region, this part is really easy. And truth be told, the hardest part of most double integrals is getting the limits of integration, okay? When the region of integration is not a simple rectangle, it gets a little bit more difficult. And that's usually the hardest part of doing these. Okay, well, then we know that the volume is simply the double integral over the region R. This is the region R down here, right? That rectangle in the xy plane. So the double integral over the region R of our function f of xy, and what is that equal to? Well, we're told that the top of this thing is part of the surface of this plane, okay? So I didn't write it here, but z is equal to a function of xy, which is 4 minus x minus y. So we're going to integrate 4 minus x minus y over this rectangular region. Pardon me. And I'm going to put a dA here, where dA corresponds to a small patch of area in our rectangular region here. Okay? When we first started talking about double integrals, we talked about this little rectangular patch, this little square patch in the region of integration, and then the volume above that up until you hit this surface up here, right? Okay, so that's sort of the general equation for a double integral. We're going to integrate f of xy dA over the region R. Okay, well, let's integrate. We got to choose a order of integration. So let's integrate with respect to y first. We can do either, but let's start with integrate y first, which means that's the inner integral, and it's the first one you calculate. So if we just write this, our function is 4 minus x minus y dy, where y goes from 0 to 1. Okay? We're integrating in the y direction. So that's our inner integral, the first one we're going to calculate. Our outer integral is with respect to x, so we just write it like that. If you want, for now, we'll just put brackets here, but very quickly we'll drop those brackets. You always do the inner integral first. So we're going to integrate with respect to y first. And the limits for x we figured out before were 0 to 2. Okay, so when we integrate with respect to y, that's the same thing as saying, let's pick a value of x here, and let's keep x constant, fixed, and we're going to integrate in the y direction. Okay, so it's just like differentiation. When we differentiate with respect to y, we make x a constant. Same thing here. When we integrate with respect to y, we make x a constant. We pretend it's a constant. Okay, so all we have to do is solve this inner integral here. We integrate with respect to y. Okay, well, the integral of 4 minus x minus y with respect to y would be 4y minus xy. We treat x like a constant, minus y squared over 2. Right? That is the integral with respect to y. And y goes from 0 to 1. So I did the inner integral, integrated with respect to y. And then we're going to integrate with respect to x later, once we've figured it out. Okay, so now we complete this. We substitute 1 for y here, subtract that, or subtract from that, the same expression with y replaced with 0. Obviously, we're going to simply get, so our volume is equal to 0 to dx, and inside here we're going to have 4 minus x minus 1/2, right? Okay, any questions so far? So same as differentiation, when you integrate with respect to one variable, you hold the other one constant. You treat it like a constant, like a number. Okay, and you'll notice, this is a dx, and you'll notice now that after we have integrated with respect to y, we've got no y's left over. There should be no y's here. We've integrated y out. We've integrated over all possible values of y from 0 to 2. So if you end up with an expression here, if you've integrated with respect to y, and you still got y's here, you did something wrong. There should be no y's left over. And now we just have a simple integral with respect to x. Okay, we've integrated with respect to y. Now we're going to integrate with respect to x. All right, this is easy. 4x minus x squared over 2 minus 1/2 x, where x goes from 0 to 2. Okay, so what do we get there? We're going to get 4 times 2 minus 2 squared over 2 minus 1/2 times 2. Zeros are all going to be zeros, so we get 8 minus 2 squared is 4 divided by 2 is 2, minus 1, so 8 minus 3 is 5. Okay, so the final result is 5. Okay? Simple, right? Okay, let's do it the other way around, just to make sure we get the same answer. This time we're going to integrate with respect to x first. Integrate with respect to x first. Okay, so we're taking the integral of the function 4 minus x minus y dx. And the limits we found for x were 0 to 2. X min was 0, x max was 2. So that's the inner integral, the first one we calculate. The outer integral, after that we do that, we're going to integrate with respect to y, where y went from 0 to 1. Okay, so from 0 to 1, dy. When I integrate with respect to x, I get 4x minus x squared over 2 minus x times y. I treat y like a constant. And x went from 0 to 2. So I'm going to get 8 minus 2 squared over 2 minus 2y. Did I do that right? X is switched with 2, so 8 minus 2 minus 2y. Yep. Okay, so I integrated with respect to x, which means all the x's should be gone. Okay, and I look at my function that's remaining, and indeed, there's no x's left here. If there's an x left in here, I did something wrong when I did the integral. Now I integrate with respect to y. So 8 minus 2 is 6, so I'm going to get 6y minus y squared, right? 8 minus 2 is 6. Integrate that, that's 6y minus, yep, where y goes from 0 to 1. So I'm going to get 6 minus 1, which is equal to 5. I get the same result. Okay? Doesn't matter which way I integrate, x first and then y, or y first and then x, I get the same result because the function I'm integrating, 4 minus x minus y, is continuous over this region. Okay, any questions about what I did there? Okay, so just to, let's have a quick look at what we actually did there. Okay, there's the same region. But in this case, we are integrating with respect to y first. okay? So if we integrate with respect to y, we choose some x value and hold it constant there, and we integrate in the y direction, which is the same as finding the area under this curve. And that curve is the function I'm integrating, okay? 4 minus x minus y, right? So if you look at it right from this perspective here, if you're looking at it straight on like this is the z-axis, this is the z-axis, this is the y-axis, and I see something like this, right? Where this here is z is equal to a function of x and y, which is 4 minus x minus y, right? And when I integrate in the y direction, I'm finding the area under this curve. Okay, that's the blue shaded part here. Okay, that's at some particular x value. So x is a constant when I integrate this, right? X is a constant when I integrate this. And then, you know, this is, so we slice through our loaf of bread like this, and then you make another slice right behind it, and the slice of that, the width of that slice is dx. You add up all those, and you got the volume, okay? Or if we integrate it in the other direction first. Okay, same thing, but this time we're going to integrate with respect to x first, which means we hold y constant at some value, and we integrate in the x direction. Okay, so if you look at it from this, again, you're going to see x, z, and we're going to see something like this. This is, again, z is a function of x, y. That's our plane. Okay, and x goes from 0 to 2. So when we integrate with respect to x, we're just finding the area under here. So this time we sliced in this direction at some particular fixed y value. You find this area, and then you integrate into y area, the y direction to add them all up. Okay, so that's all we're doing. Any questions about that example? Okay, well, what if the region of integration is not rectangular? Well, things get a little bit more complicated. Non-rectangular region of integration. We just got to work a little bit harder. So there's a few steps you should follow. Pretty much any type of problem you have to do, if you're not given a sketch of the region of integration, you really got to sketch one yourself. So for those of you who are not artists like me, you're going to just have to bite the bullet, do a little drawing, sketch the region of integration. Because often, you're just given an equation that describes the region of integration, or some words that describe it, okay? It's really in your best interest to draw it, okay? So sketch the region of integration and label the curves. Label the curves mathematically. Don't just give them names. Find the equations that represent the boundaries of this region of integration. Okay, so the example we're going to use, our region of integration, we are told is bounded by x plus y equals 1 and x squared plus y squared equals 1. That's all we're told. Okay, so the region of integration it's a region in the xy plane, and it's bounded by curves or lines. Obviously, x plus y equal to 1 is a line. X squared plus y squared equal to 1 is obviously a circle. Okay? So we're going to draw the region of integration in the xy plane. Part of it is bounded by a circle, so we'll just draw the whole circle. X squared plus y squared is equal to 1. Okay, that's the circle. X squared plus y squared is equal to 1. And x plus y equal to 1 is a line. So when x is equal to 0, y has to be equal to 1. So this is 1 point on the line. And when y is equal to 0, x has to be equal to 1. So this is another point on the line. So my line looks like that. Okay, that's the line x plus y equal to 1. And my region of integration is bounded by those two curves. So in that case, my region of integration, oops, that's the eraser. My region of integration is right there. Okay, that's my region of integration R. So that's step 1. Step 2, decide on an order of integration. Am I going to integrate with respect to x first or with respect to y? Well, that depends on the region R. In some cases, it'll be easier to integrate in one order. In other cases, it'll be easier to integrate in the other order. In some cases, it doesn't matter, okay? And this is a case where it doesn't really matter, because if I choose a y value and hold it fixed, and I integrate in the x direction, okay, that's really no different than if I choose an x value, hold it constant, and integrate in the y direction. It looks very symmetrical when I pass through this region of integration. If I integrate in the x direction, it looks like this. If I integrate it in the y direction, it looks like that, right? It looks the same. I enter the region of integration along this line. I leave it through the circle. Same thing here. I enter at the line. I leave through the circle. So in this case, it really doesn't matter. But in other cases, it'll just be easier one way or the other. And that just comes from practice and experience. There's no hard and fast rules to tell you what that is. You just have to do enough of these problems before you get that, okay? Okay, so I don't know, we're going to, let's integrate y first, then x. Okay, I'm going to draw my region of integration. Pardon me. I'm going to draw it just a little bit bigger. Okay, so we're going to integrate with respect to y. So that means I'm going to fix x at some value, and I'm going to integrate in the y direction. So to represent that, I'm going to choose some value of x here, and I'm going to integrate in the y direction. I'm going to draw a straight line, an arrow, going through my region of integration to represent that I'm holding x fixed and I'm integrating in the y direction. And I ask myself, where does that arrow enter the region of integration, and where does it leave? Okay, it's going to enter at y min, and it's going to leave at y max. I'm integrating in the y direction, okay? X is held fixed. Okay, now at some point I'm going to integrate in the x direction too. So I have to ask myself, well, what if I pick a different value of x and integrate in the y direction? Say I hold x fixed here and I integrate in the y direction. Well, obviously in that case my y min is going to be here, and my y max is going to be up here somewhere. So you'll notice that y min and y max change depending on which value of x I choose to hold fixed at in order to integrate in the y direction. Okay, so that means y min and y max are not going to be numbers. Because if I drew this arrow over here, y min would be here, y max would be here at some values. If I draw my arrow like this, y min is here and y max is here. They're smaller values. If I draw my arrow here, y min's down here, y max is maybe here. Even smaller values. So that means y min and y max are not going to be numbers. They're going to be a function of x. Depending on what x value I pick, I get a different y min and a different y max. Okay? So y min and y max are going to be functions of x. And I need the mathematical equations for these boundaries to tell me what those functions are, right? This one here is x squared plus y squared equal to 1. This one here is x plus y is equal to 1. So that means, let's deal with the y min value first. That means everywhere on this line, what is y equal to? Y would be equal to 1 minus x, right? I choose some x value. Y would be 1 minus that value. That would be this value of y. If I choose this value of x, well then, for this value of x, y will be 1 minus that value. It'll be something smaller. Okay? So that means y min, no longer a number, it's a function of x. It's going to be 1 minus x. Okay? Same thing with y max. I ask myself, what is the value of y when I leave the value of the region of integration? Well, it's going to be this. That also is going to depend on what x value I choose to hold fixed at, right? So y max will also be a function of x. So, and it's going to be described by this. So in this case, y is going to be equal to 1 minus x squared, square root of that, right? So y max is going to be 1 minus x squared square root. Now, really it's plus or minus that, but which is it going to be? Y is always going to be positive, right? This is the first quadrant. My region of integration is in the first quadrant, so y is always going to be a positive number. So I'm going to choose y equal to positive 1 minus x squared square root. Okay? So y min and y max are functions of x. Any questions on how I got those? Okay, so I'm integrating with respect to y first. So, you know, I'm going to have some function of xy dy where y goes from 1 minus x squared to 1 minus x. So that means I integrate with respect to y, right? I end up with some expression that only has x value, well, no, it has x's and y's in it after I do the integration. And then when I apply these integrals, limits, to the result of doing this integral, I substitute all the y values in this expression that's left over when I've done the integral. I substitute every y with first this, and then subtract that from that expression where every y is substituted for this. We'll do an example, okay? So that gives me my inner integral, okay? All right, now I got to integrate with respect to the, I probably skipped ahead to, yep. Okay, so I found my y limits for the inner integral. Now I need to find x min and x max. Okay, so yes, sir. Sorry, I have what? Yep. Oh, I switched them. I'm sorry. Yeah, I can't erase anymore. Y min is 1 minus x. Y max is square root of 1 minus x squared. Thank you. Don't let me get away with garbage like that. Perfect. Okay? Okay, now I'm going to integrate with respect to x. The outer integral, the second one that I do, is integrating the result of the inner one with respect to x. And again, once I've completed this integral and I've applied these limits to it, I'm going to end up with some expression. It's only going to have x values in it. There's going to be no y's left because I've integrated in the y direction. Once you integrate in the y direction, y's gone. Okay, so after I finish this integral, apply these limits, I should be left with some expression of x only. If there's a y in there, I screwed up. Okay? Okay, so what x min and x max, how do we find those? Well, the easiest way to think about this is I'm going to take this line that I drew and I'm going to redraw it so it just enters the region of integration on the far left-hand side. So let's use a different color, red. That means I'm going to draw it like this. Okay? And now I'm going to scan through my region of integration from left to right with that vertical line. So I scan through in this direction until I end up right there. And I ask myself, at what x value does that vertical red line first enter the region, just first touch that region of integration as I sweep it from left to right? Obviously at a value of x is equal to 0, right? I mean, if I draw it over here, it's not touching the region of integration. So I keep pushing it to the right until it first encounters that region of integration, because I'm only integrating over this region. That happens at a value of x is equal to 0. So my x min is 0. X min is 0, a donut, okay? And I ask myself, okay, I'm going to keep scanning right through, sweeping right through my region of integration from left and right with that vertical red line. And I ask myself, at what x value does that red line just leave the region of integration? It's going to be at an x value of what? Well, right here, which is x is equal to 1, right? So x max is equal to 1. Okay, so now my complete integral, f of xy dy first, then dx, y is going to go from 1 minus x to the square root of 1 minus x squared. X is going to go from 0 to 1. Okay? That's I've got my integral set up now. So again, I'm going to do the inner integral first. I'm going to integrate this with respect to y, which means hold x fixed, integrate with respect to y. You get some expression, apply the limits. Right? You substitute first all the y's left in this expression with this, subtract from that the same expression where all the y's are substituted with this. Now I've got some expression just with x in it. Now I take the integral of that expression with respect to x and apply the limits from 0 to 1. Okay? So this is the general case, and you'll notice that the limits of our inner integral could be, and in this case they're functions of x, the variable that I'm not integrating with respect first. Okay? But the outer integral limits always, at least in this course, are numbers. Even if it's not a rectangular region of integration, this is not rectangular, but they're always numbers. And why is that? Because after you do the outer integral, there's no more integration to be done. All the x's and y's have to be gone. You have to be left with just numbers. If I have x's or y's in here, well then I'm going to end up with a result of this double integral that has x's and y's in it. That doesn't make sense, right? It's a definite integral, which means the end result is a number. Okay? So when you're setting up these double integrals, the inner integral, if it's with respect to y first, depending on the region of integration, these limits, they could be numbers, but they could also be functions of x. They better not be functions of y. Otherwise, after you finish this inner integral, integrating with respect to y, you'll have y's left over, which doesn't make sense. When you integrate with respect to y, all the y's got to be gone. And then when you integrate with respect to x, all the x's got to be gone. And you should be just left with numbers. Okay? Okay, so and if we went in the opposite direction, let's integrate in the opposite order. Same example. Okay, we got the same region of integration, x, y. This time we're going to integrate with respect to x first. Okay, which means we choose some y value and hold fixed there. I don't know, maybe right about there. Could be any y value such that when we draw this arrow through the region of integration, it actually goes through the region, right? I wouldn't pick a y value here and go like that. Doesn't go through the region of integration. That's useless to me. I pick a y value such that when I draw this line and I integrate in the x direction, I go through the region of integration. Okay, and I say, okay, I'm integrating with respect to x first. I'm looking for x min. I'm looking for x max. Again, depending on where I draw this line, this arrow through my region of integration at different y values, I'll get different x mins and x maxes. So that means x min and x max have to be a function of y. They depend on where I choose to draw, at what y value I choose to draw this horizontal arrow. Okay? Okay, we've got the same curves here. This is x squared plus y squared is equal to 1. And this is, what was it? X plus y equal to 1, right? Yeah. X plus y is equal to 1. Okay, so what's x min going to be? Somebody want to venture a guess? It's where that arrow enters that region of integration. At what x value? Yeah. 1 minus y. We got one answer for 1 minus y. Anybody agree? Lots of head nods. You must be right. Or you're all wrong. No, you're right. What's x max? Well, it's where that line, it's the x value where that arrow leaves the region of integration, which is along the curve x squared plus y squared is equal to 1. So obviously those x values are equal to 1 minus y squared, square root. Again, I would choose the positive value, not the negative one, because I'm in the first quadrant. X has to be positive, right? Okay, so that means my inner integral is going to be 1 minus y to square root of 1 minus y squared of my function, whatever it is, we're not told what it is, dx, integrating with respect to x first. Notice that the limits are functions of y. So after I've finished this integral, I'm going to end up with some expression with y's in it. All the x's better be gone, because I integrated with respect to x. They got to be gone. So I'm only left with y's. And now the outer integral, so again, I'm going to sweep this arrow through the region of integration in the y direction, because now I'm integrating with respect to y, from the lowest y value to the highest y value. And I'm going to say, okay, where does it first touch that region of integration? Well, when I draw it right there. That gives me y min, which is obviously equal to 0. And now I sweep it upwards in the positive y direction, because I'm integrating with respect to y. And I ask, where does it leave? It leaves when I draw it right there. Okay? And that was at the value 1, because that circle, x squared plus y squared is equal to 1, has a radius of 1. Okay? So now I've got my double integral. Right? I solve this inner integral. I end up with a function of y, no x's. Then I do this integral, and once I've applied these limits, I get all the y's are gone, and I got a number. The result is a number. It's a definite integral. Okay. All right, let's do an example all the way through. And the lines y equals x and x equals 1. Okay, so we're supposed to find the volume of a prism whose base is a triangle in the xy plane, bounded by the x-axis and the lines y equal to x and x is equal to 1, and whose top lies in the plane z as a function of xy3 minus x minus y. And this is very common for these problems. Often you're not given a picture, you got to figure it out for yourself. So we've got some three-dimensional prism, and the base of this prism is a shape in the xy plane, okay? That region, and so what is the region of integration? What is the function we're integrating? Well, the function is going to be the top of this prism. We're finding the volume underneath the top of this prism. That prism top is represented by this surface, 3 minus x minus y, it's a plane. And the region of integration, it's going to be a triangle in the xy plane, 3 sides, so it's bounded by 3 lines, the x-axis, y is equal to x, and x is equal to 1. Okay, so step 1, we're going to sketch the region of integration first. It doesn't have to be a work of art, right? It just has to be good enough so that you can make sense of what the limits for x and y are going to be. Okay, so the x-axis is one side of the triangle. The line y is equal to x. Well, that one is easy. That's just this, right? That's y is equal to x. And x is equal to 1 would be, look something like this, right? Where this is the value of 1, which means this also has to be 1, since that's a point on the line y is equal to x. So this is my line, x is equal to 1. This is my line, y is equal to x. And obviously the horizontal one is the x-axis. Okay, so my region of integration, R, is that triangle. Okay, we got to decide on an order of integration. It doesn't matter too much with this one again. In fact, it doesn't matter at all. The amount of work is the same either way for this region of integration. If I integrate with respect to x first, that means I'm drawing a line like that. If I integrate with respect to y first, that means I'm drawing a line like this, right? It's kind of symmetrical going through this region of integration. Doesn't really matter. Which order do you want to do it in? X or y first? Somebody shout out x or y. Y. Thank you. Integrate with respect to y first. Good practice would be for you sometime on your own, do the same problem, integrate with respect to x first. Make sure you get the same result. Okay, integrate with respect to y first. That means we choose an x value, we hold it fixed, and we draw a line in the positive y direction because we're integrating with respect to y. So something like that, oops, something like that. Okay, we're integrating in the y direction at that value of x. And we ask, okay, where does that arrow enter the region of integration and where does it exit the region of integration? At what y values? Keeping in mind that I could have drawn this line, I could have drawn it over here, I could have drawn it over here. So let's look at y min. What would y min be for any of those vertical arrows that I drew? Where do all 3 of those arrows enter the region of integration? At what y value? 0, right? Doesn't matter where I draw this arrow, y min is always going to be 0 because my region of integration is bounded by the x-axis here. They're all going to enter the region at a value of y is equal to 0. So y min is a number. It's 0. Okay, what about y max? Well, that's going to change depending on where I draw my arrow through the region of integration. It depends on what x value I draw that arrow at. So it's going to be a function of x, right? It's going to be, and what is that function of x? Right here. It's It's this boundary, this curve, this straight line. If I choose this value of x, y max is going to be that value of x. If I choose this value of x to draw my line at, y max is going to be x, okay? So what's my y max? Simply x, okay? It's a function of x. I'm integrating in the y direction, so it's either a number, like y min was, or it's a function of x. Okay, so far so good. And now I say, okay, I'm going to sweep this line of, I'm going to integrate in the x direction, so that means I'm going to take that vertical arrow and I'm going to sweep it from low x values to high x values through the region of integration. Okay, if I draw that arrow there, that's where it first touches and enters the, right? It first touches right here, the region of integration. That happens at an x value of what? 0. So x min, x, is equal to 0. What about x max? Well, that's where it just leaves the region of integration, which would be right there. Right? I take that red line and I sweep it from left to right. And what x value is that? Obviously 1, right? This is the outer integral limits. They've got to be numbers. Okay, so I've got my limits, so I'm going to integrate with respect to y first, pardon me. The function was what again? It was 3 minus x minus y. 3 minus x minus y. I'm integrating with respect to y first, so y min is 0, y max is x. My outer integral, with respect to x, its limits are 0 to 1. So first I'm going to do the inner integral. Always do the inner integral first. So I integrate with respect to y, which means hold x constant. So I get 3y minus x times y minus y squared over 2, where y goes from 0 to x. Okay, so now I've got 3 times x minus x times x minus x squared over 2 minus 3 times 0 minus x times 0 minus 0 squared over 2 . Okay, I'm doing the inner integral, integrating with respect to y, so you'll treat the x's as constant. Then I substitute in the limits, right? Take this, substitute x for all of the y's, subtract from that the same expression with all of the y's substituted, or 0 substituted for all of the y's. 3 times x minus x times x minus x squared over 2 minus 3 times 0 minus x times 0 minus 0. Right. That gets rid of all the y's because I'm integrating with respect to y's. All the y's got to be gone. Once I do this, I'm left with what? I'm left with 3x minus x squared minus x squared over 2, which is minus 3 over 2x squared, right? I did that right. Okay, so I'm done the inner integral. I'm left with an expression only of x's. Now I take the integral with respect to x, 3x squared over 2 minus 1 over 2x cubed, where x goes from 0 to 1, gives me 3 over 2 minus 1/2, which is 1. Okay? Again, good practice. Change the order of integration. Do it yourself. Figure out x min, x max. They're going to be functions of y. Then find y min and y max. They're going to be numbers. And do it yourself. All right, we'll see you Wednesday.